Hi everybody. So we are leaving now our algorithms and the complexity of algorithms alone for a while, and we move into a new chapter called number theory and cryptography, because it's especially the cryptography that's kind of our goal here. And remember what the trying to keep you a little bit keep the bigger picture a little bit in mind. What is it that we're trying to do? Remember, we had this distinction between tractable and intractable algorithms. And what we wanted to do then is use that somehow, the intractability, use that to encode things that cannot be decoded easily. But of course, it's not that nobody can decode it, because then it's useless. If you have some extra information, which we sometimes call a key, you can decode. And for that, we needed algorithms that, not necessarily, but you'll see these are the kind of algorithms we kind of start thinking about, are the so-called non-deterministic polynomial time algorithms. They themselves are exponential, so that it's very hard to solve them, but non-deterministic polynomial means that if you have an answer, you can check it. And that's what we want to do, right? So if somebody sends an encoded a password, the receiver, the website that receives this password, has to authenticate the person, so it has to calculate and verify that this password is the correct password. If that also takes exponential time, forget it, it doesn't work, right? So now, why do I bring this up? What in Earth this has to do with this topic that is called divisibility in modular arithmetic, is because it will be the source for us of these algorithms. Now, that's not the only source, but historically one of the first sources is also one that is more easily explained. And we'll go there. We will use the encryption methods that nowadays are still prevalent, although we are a bit worried about cryptographic attacks against them, but that all for later. So we need to talk about this technique that is called modular arithmetic. Arithmetic, I hope that you have some idea, this means adding, subtracting, multiplying, and division. That's the four operations of arithmetic. So what is this modular? What does that mean here? And before I do that, there's this other term, divisibility. Now that's something that you know, of course. If you have two integers, a and b, so these are integers. Remember, I'm going to use our fancy notation for integers, so they could be negative. I can look at the quotient, and that would of course in general be a rational number. This is our fancy notation for rational number. But sometimes if it's a rational number, it means in a decimal expansion there's a decimal. Okay, so there is something after the period. But if sometimes it doesn't. So if we have 10 divided by 3, yeah, that will belong something like 3.333, or 10 divided by 4 would be 2.5. The decimals, it can be just a single decimal, but it is a decimal, okay? So, but sometimes it isn't. So if we take 10 divided by 2, that is 5. That is now an integer. So we say that a is divisible by b if a divided by b is an integer. Okay, and or we say b divides a. So we can turn the order in which we say it is, if you want, for those that like grammar, one is the passive and the other one is the active form of dividing. So b divides a, and that we normally, it's this version, this direction that we denote this way, by a kind of longer line that kind of goes below the line that we write on, and it's a vertical line. It's a bit a nuisance as a symbol because it's sometimes very illegible. It's kind of like a line. Okay, lines are used for so many things, right? So, but in this context, it means b divides a. That means, so in this, so how would you formulate this? This says that 2 divides 10. Not 10 divides 2, but 2 divides 10. Okay? Another way of saying this, b divides a, also b is a divisor. Is a divisor Sometimes we also say factor of A. So there's a lot of terminology that expresses always the same fact. Okay, so that is kind of obvious what this means. However, let's try to formulate it a little bit better, because I'm going to do a little bit of proofs. Oh, no proofs. Yes, we have to practice our proofs. That's what we started with, right? So we're going to keep our... don't forget too much about what we did originally, so let's do a little bit of proofs. But in order to do that, we have to write out what it means to be a divisor, or to divide what this operation means. And it's all in this part here, right? So B divided A means that A divided by B is some integer m. And so now I can do some small manipulation. It says that A is equal to m times B for some integer m. So there is an integer m such that A is m times B. In other words, you see here better the idea that B is a factor of A and m is the other factor, okay? But this allows me to write, so when I have this B line A, what can I do with that, okay? And let me immediately give you a proof. So theorem, it's not really a theorem, so that is me theorem or property. If A divides B, and let's see what I want to say here. There's so many. A divides B and A divides C. Then then A divides B plus C. Okay. Well, it's perhaps not immediately clear that this is true, but we will prove it. And it is an if-then. There are many ways of doing it. We can do contraposition, we can do contradiction, but this is just a simple direct proof. So I'm going to give a direct proof of this. If you don't remember anymore what the direct proof is, well, shame on you. Well, no, not really, of course. I cannot expect you to remember everything of this proof, but please go look it up. Okay? So direct proof, A divides B. Well, as I said, what can I do with that? How can I manipulate that? Well, I can manipulate that by encoding it this way. This means that A is equal to m times B, or B times m, because the order in which we multiply is not important, for some integer m. So we are, if you want, decoding or translating what this symbol means. Now, that's not, remember, what's the direct proof? You assume, let me set it as a direct proof says, assume the hypothesis, A divides B, and also A divides C, and then to show is that A divides B plus C. Can I test you quickly on something that we discussed about these proofs? What are A, B, and C here? Well, they're integers, but which ones? So remember that when we make statements where we call these general integrals, that actually there is a universal quantifier in front of this. This is for all A, B, and C. So we're actually saying for all A, B, and C that are integers, this is true. And then in a direct proof, we are allowed to take arbitrary A, B, and C, and then argue with these as pretending these to be specific elements, although we don't know what they are. Okay, just getting back a little bit on the mechanics of our proofs here. But sure, let's not dwell on that, because if I didn't mention it, you wouldn't have known that there was some issue here. But there is no issue. But okay, so I have now. So this is I have assumed A divides B. I have used this information. Let me do this in a different color here, or let me do this. Oops. No, I don't want to talk to you. A, B. What about this information? Well, okay. A divides C means that A is equal to... Should I write MC here for some integer m? Why should I not do that? Because I have no idea that remember, what is this m? Was a quotient, right? Of A divided by B. Why would the quotient of A divided by B be the same as the quotient of A divided by C? Well, if B and C are equal, yeah, sure. But other than that, no. So I cannot use the same m here. I should put a different number here, and n. Now, I know you guys think that what I just wrote down as an M and the thing that I wrote above it, you don't even know what it is. Remember, I told you, you have to get used to my writing. 3 bombs is an M and 2 bombs is a N. Okay? So, okay, for some integer N. Okay, use different names for that. Now, what is it that I need to show is this, which also translates into a statement about A and this side, and what should be then on the other side? Well, this M that we don't know yet what it's going to be. Remember, this is something that we don't know yet. But on this side, not B, not C, but B plus C. But that's not so hard to do, right? Look, let's just, wait, what I'm trying to say here. No, oh, sorry guys, if A divides, what is wrong? What is wrong? I put it in the wrong order, right? I was thinking, how does all something get? A divides B, that doesn't mean that A is M times B, it means that B is M times A. And I'm so sorry for that, because I was looking, I'm sorry, it's sometimes if you're looking at one thing, then you see this thing and you should have seen that thing. So, okay. A divides B means that, okay, this is something you have to get used to. The smaller guy is on the left, so that means B is A times M. And what is the same thing? Then C is A times M. Okay, this is a mistake that you're gonna make. You see, I make it. So you have to be very careful with that and say, okay, this is always the smaller guy. This is the one that goes inside that guy. So it's the one that is gonna be the factor, right? This is the factor, if you want. This is the big guy. So this is the factor, this is the factor. A is twice this factor here. But the other, this quotient here is in general different, so we have to take an M and a different letter N there. But now we have to talk about B plus C. Well, let's just add them up. So B plus C is AM plus AN. Now what I want is somehow, remember something of the shape, that this B plus C has this guy as a factor. So I have to establish this or exhibit this one as a factor of B plus C. Well, let's just factor out A, and there it is. This is the factor. Now here you see A is a factor of B plus C, which exactly means this. Okay, all right. And there are many other things. I'm going to leave some of them as homeworks for you to explore and to try out. The next thing that we need to do, and that's a very important tool, and we're going to use this a lot, so make sure that you understand how this is, works. This is called the division algorithm. We will write later the pseudocode for it, but for now I'm just going to explain what we do here. It's also sometimes the Euclidean division. Euclidean division, already, because it already appears in the books of Euclid. The Greek Euclidean, that's with an I then, I guess. Many centuries ago, I mean, more than 2,400 years ago. Okay, so this division algorithm works, but again, my wife is a historian and she would find me remiss if I don't tell you this. It's not Euclid who invented this algorithm. This was known by the Babylonians, by the Persians, the Indians, the Egyptians, all knew how to do this, or to some extent. But it appears in the books of Euclid, and of course it appears much later in many other writings. We talked about Omar Khayyam, perhaps, as one of the founders of algebra. He describes this too in his book. Okay, so going back, what does this say? Well, with the idea is we want to divide an A, so this is an integer. So the goal is to divide A by another integer D. Now, I'm going to make my life a little bit simple, and I'm going to assume that D is actually positive. First of all, I should not divide by 0, so it should not be 0, but I'm not going to use negative numbers too. There's some things about negative numbers that the textbook will is a bit more explained there, but we will not really use them as much, so I'm going to restrict to the cases where we need that. Okay, so A is an integer, so that could be negative, but again, for us it's going to be normally a positive number, and we divide it by d. Now you say, okay, that is A divided by d, that's what you mean, right? So, okay, if you do 10, let's say, an example, so let's do an example, right? Well, I had it here is the example. 10 divided by 3, well, that's this. What that's the division. What division algorithm are you talking about? Well, I would like to have, what I want to do is long division. Oh, there we go again, long division. So we have 10 here, right, and here 3. How many times does 3 go in 1? Not, but 3 goes in 10 3 times, and the result is 9. Sorry, I wrote it the wrong way. Sorry. Yeah, I make these mistakes all the time with long division because I've learned it the other way. So, okay, it goes in there 3 times, right? This is the quotient, but then 9. So if we subtract 1, how many times it goes 3 into 1? Sorry, let me get rid of this writing here. Okay, you're following here what I'm doing. So you subtract 1. So how many times does 3 in 1? It doesn't go anymore. So this is the end of our long division, unless we keep going and we want to have the decimals. If we want the decimals, then we would have to put the decimal and put an extra 0 here and keep doing. That's why my 3.333 came from. But I don't want to do that. I don't want to work with decimals. So I want to stop here. But how do I gather this information? Well, the information is that 10 is equal to 3 times 3, and this, what we call that, the remainder, right? So this is 1. This is called the remainder. And then this we call normally the quotient. So typically, when we carry out a division, a long division, we have a quotient and a remainder. Now, sometimes if we don't have a remainder, of course, if we do 10 divided by 2, then that would be 10 is 2 times 5. So 5 would be the quotient plus 0, no remainder, right? If I want to write it in this fashion, well, I'll write with an x here, but that's right with the multiplication dot. So that is something that we can do in general. And the statement, therefore, in general is, let me not do a special case, that we can write A as there's a quotient Q, so Q will be the quotient. We will introduce a new notation shortly. And a remainder, R, is the remainder. This is how I write my R's. Again, I apologize, but this is what I'm used to, and I cannot change myself that easily. So, now what is a remainder has to be? Well, when we do long division, a remainder, so if I would have found here remainder 4, then I could still continue 3 into 4, right? So for instance, let me show you what I mean here. Suppose I'm going to do 40 divided by 3. Okay, then we do 3 goes into 4 one time. We subtract 1, then we bring the 0 down. 3 goes in 10 3 times. So that's 9, and then we subtract 1, and 3 goes in 1, it doesn't go anymore. So this is the remainder now. So in other words, we keep going until our remainder is smaller than the number we divide by. Because if it's bigger, like in this case, 10 or 4, we can divide, we can take it out, at least once or twice, or perhaps many times. Okay? So the remainder, therefore, has to be smaller than the number that we want to divide by. That's the d here. And of course, again, the remainder should be positive. So this is the constraint that we have of our remainder. And the quotient could be anything then. Okay, but of course it has to be an integer. Okay, so for instance, let's do 101 divided by 11. So how would that work, right? Okay, so we do long division. 101, 11. How many times does 11 goes in 10? It doesn't go, so we have to go, if it doesn't work, then we have to look for the next digit. Well, we should do perhaps how many times does 11 go into 1? Not. So how many times goes 11 into the first 2 digits? Not. How many times goes 11 in the first 3 digits? Well, it goes there 9 times. And the result is 99. And what if we subtract, we get 2. And how many times now does 11 go into 2? Not. And there are no digits to break down anymore, so this is the end of our calculation. So this would mean that 101 is 9 times 11 plus 2. So 9 is the Q and 2 is the remainder. Okay, so let's introduce notations for this, because we're going to use this so often that we want a notation for that. And so these are functions that most calculators, especially online calculators, have this. You have to sometimes look a little bit for it. There's not necessarily the immediate display. There might be like a second function or something like that. But here are the two functions that I want. So the function that calculates Q, and we will write this A, and now I have to write this in a different font size. I should include, okay, let's see where I can. Sorry guys, I'm gonna add this guy to my favorites. There he is, but how do I distinguish him from the others? Let's make, no, I didn't, that's too late now. Okay, so okay, here. So, okay, it's will written div, so boldface, D. So that is Q. So div is a function, but a bit strange. We put one thing at the left and another side on the right, a number, right? A div D, A divided by, and so this is perhaps a little bit confusing, that while division is when we say B divides A, it's B is the smaller one, goes into A. But here A is the bigger one, and we divide A by D, or by the B over there. Okay, so that's what we write here. Now, how do you write denote the remainder? So some use rem for remainder, but we will use something that is actually more common, mod D. And mod here is short for modulus, and modulus is a word that is used for a remainder. And so this is also the root of this term here, modular arithmetic. And as we will see yet, I'm not there yet, but so okay. So let's rewrite this information that I got here from this division here. Let's do perhaps another one here. Let's do 120 divided by 11. Sorry. So I'm used to write it my way, so I'm going to do. So I want to calculate the following things. What is 120 div 11, and what is 120 mod 11? Okay. So I'm going to show you two ways. First we do long division. So we can do the long division. Okay, so we have 120 and divided, was it 120? I thought I said 140. I want to do 140. No, 120 is fine. Okay, 120 divided by 11. So we say, how many times does go 11 in 1? No. How many times goes 11 in the first two digits? 12. Yeah, that goes there one time. So we multiply. So what we do, of course, we multiply this with that. We put that here and subtract. The result is 1. How many, to bring this 0 down, how many times does 11 go into 10? Not. So be careful, we have to put a 0 there. And this means, therefore, that this is our remainder, because there is no 0 to bring down anymore. But don't forget that we have the extra 0 here, right? So the result here, therefore, this means, write it down in the form, in the form of the theorem, the algorithm here. If you want, it's more of a theorem than an algorithm, but okay. Is that 120 is 10, that's the quotient, 11 times 11 plus 10, that's the remainder. There are two 10s here, but this 10 is the quotient, this 10 is the remainder. Okay, perhaps that was why 120 was not a great choice, but all right, I did it. Okay, so let's write this up. This means that this is 10 and this is 10. Okay, let's perhaps, let me do a different number, that way we see they have different values. Let's do the same question, who are 140, okay? So I'm doing the same question, and then I'll show you also the second method, which is much shorter, by the way. Of course, the shortest of all method is if you just have a calculator that calculates it for you immediately. But I want you to be able to do this without such a calculator. Although I will allow you to use these calculators. So on quizzes I might say, show me the calculation of this div and mod, and then this is what I'm going to give next. Or you can just calculate it in cases where we need, when it's just one of the intermediate calculations. Okay, so the long division, let's do the long division. So this is method 1. But as I said, it will not be our preferred method. But I still want to explain to you how it works. So 140 divided by 11. I don't know why I keep using 11, but okay, I did it now. So how many times does 11 go in 14? One time. 11, so 3. Bring this down. How many times does 11 do in 30? Twice. So bring it. That will be 22. Bring it down 8. How many times goes 11 in 8? It doesn't go anymore. There's nothing to borrow. So that's it. So we see that 140 is 12 times 11 plus 8. So this is my Q, this is my R. So this is 12, this is 8. Okay, that's method 1. Now, method 2, as I said, will be much quicker and also more calculator oriented. So method 2 is using the calculator, but not the fancy calculator that calculates mod and diff. Method 2 is a basic calculator. In other words, it doesn't have any of this fancy stuff, but it does calculate 140 over 11. Now, I'm not going to show you the calculation because everybody knows how to use a calculator, right? So 140 divided by 11, according to my calculator, this is 12.7272 and so on. So let's write. In fact, there's only one digit I really need to know. So 12.72. The first in these cases, what we need is the first non-zero digit, if you want in this calculation. So what do we do then? Well, then, so this is step 1. You calculate with a calculator. So this is using a calculator. Using this basic calculator, we calculate this number, the decimal expansion. Step 2, we take this floor. So we take the floor of this thing, which therefore is, in other words, is ignore the decimals, it's 12. Okay, so this is already the 12 that we get here. Now comes the trickier part. What is the remainder? Well, look at here, where is the remainder come from? Oh, I erased this, but let me write it up again. Remember that my first calculation showed me that 140 was 12 times 11 plus 8. Notice that this actually is a way of calculating the remainder. If I know the quotient, I know the remainder because I just bring this to the other side. 140 minus 12 times 11 is 8. Okay, so step 3 is the remainder. What you do, you take the original number, 140, then subtract from it 12 times, that is what you just calculated here, this number, times 11, that's the divisor. Okay, so that is 140 minus 132, which is 8. And that's where my 8 comes from. Okay, let's do this on a little bit more challenging problem. So let's calculate. I'm just going to write the number 14000. This number I want to calculate mod, because very often, and you will see, we actually are not so much interested in this number. Sorry, let me do this with circling. We're not really interested in the diff, in the quotient. We are interested really in the mod, modular arithmetic, right? So that's why. So we want to calculate this, for instance, say of 431. Now, long division already gets a little bit tiresome here, right? Cumbersome here. So how would I calculate this? So, okay, here are my steps. Step 1, I do this with a calculator. I calculate with my calculator 208 divided 431, and that is equal to 143,208. 143,208 divided by 431. That is 332.26 or 0.28. Step 2, I now know what 14328 div 431 is. That is the floor of what I just found. So that is 332. So now, what is the mod? So I'll write down the formula now. This is the formula. So I'll write down here the formula, right? So what I said here, let's write this out a little bit in the general formula. The remainder, which is therefore A mod D, what is that? Well, you take A, and from it you subtract what? The product of your diff and your divisor. So D times A diff D. Let me see. Let me point out. So in order to calculate A mod D, what I have to do, I first calculate A diff D. That's this number. Then I multiply that number with the divisor that I used, D. Right? So I try to get back to the original number. If this would be divisible, so what? Yeah, remember, what does divisible mean in our previous setup? Divisible, remember, divisible by this thing means that the remainder is 0, right? So this means that this would be 0. This means that these two things here, this thing would be equal to that. There would be no remainder, right? What is it here? That there would be no remainder. This would be that. So what I'm doing here is exactly recalculating this. This is the divisor, this is the Q, this is D. So this is the D times Q. And I'm subtracting this from A. And if the remainder is 0, then this will just be A. But in general, there will be a remainder. So this means what now? This means that for our purposes here, 1, 4, 3, 2, 8 mod 431 is what? Well, we take the number 1, 4, 3, 2, 8 and subtract from that this product. One is the original divisor, that is a 431. Oops. 431. So let me outline. So this 431 is the one. Is this one here, right? We multiply that with our diff, which is the number that we calculated here. That is this number. That is the result of this. This is this calculation. So we put that here. So this will be 332. So we multiply these two numbers, 431, 332, and subtract it from 14328. Okay, let's do that. 431 times 332, that is, so this number, if I calculate, my calculator is 143092, and now I subtract this from my original number that I want, this big number. Okay, so let's do that. So minus 143,208, and I get 116. Oops, 160. Just do that with a calculator. Okay, you can verify this. I hope you take your calculator with you next to you, and as I do this, do it yourself as well. Okay, so that's how we calculate a mod. Unless we, as I said, some of these calculators allow you even to just calculate directly. But I want you to, for now, not to do that. I want you to do it this way. So in the homeworks and so, and perhaps in the quiz and so, this is now the way that you have to calculate it for me. Now, I should warn you that, as I said in the textbook, they do discuss what happens if you take negative numbers and divide. In other words, if this number would be a negative, then you have to be a little bit careful. Then you don't take the floor. This was not the floor, guys. This is a kind of little. The floor should look like that, right? But you have to take the ceiling. I don't want to discuss that because we're not going to do that. Okay, so let's not discuss. Not go there. Okay. So now we are kind of now ready to talk about modular arithmetic. And what is this? Well, we will work with, we will add and multiply. We do basically the same operations. Division is going to be the tricky part, so let's wait with that. As with regular numbers, except that we're going to keep taking this mod operation with a fixed number. So modular arithmetic is always modulo, a certain number. So in here, when in my last calculation, that modulus was 431. So I was calculating basically this number modulo 431. And in other words, that was the remainder. So modular arithmetic is to put it somehow in between parentheses, between quotes. It's not really that, but it is calculations with remainders. So always we calculate with the remainders, not with, it's only the remainders that we are interested in. So calculations with remainders. Okay, so and first of all, this is not new for us. We should not be too surprised about that. So here, let me give you some examples where we are doing this in daily life. We normally don't do this, I agree. Mostly we always we just do the regular addition, but it's not that this is completely unknown to you. Okay, so suppose this here. We have, let's say, a camera. Okay, this is a camera here. It's positioned somewhere here, and it's on a turning style. It can be turned around, and so the camera at this moment, let's say, is, or a cannon. If you want to be a bit more military-like, let's put it, make it a cannon. Okay, I'm going to make it a cannon. Okay, so here's my cannon, and it's pointing in a certain direction. In other words, I'm measuring this direction as with a degree. So this is a certain angle it has with a fixed line. So I'm sorry, I'm thinking of this not as, I'm thinking of this as a two-dimensional plane, and it can rotate 360 degrees, right? So this is north, this is east, south, and well, this is west, and this is south, east, right? So think of it that way. So I'm looking on top, above, on the thing that is mounted on a thing. So it can go 360 degrees, okay? So let's say in this big picture, it looks like it's about, I don't know, 60 degrees. Let's call it 60 degrees. So I'm gonna put it here at 60 degrees. So let's say 60 degrees. Okay. And now I want to turn around. So I want to give instructions to this. Let's say I'm operating this remotely through a program, and I want to tell the thing, okay, sorry, Canon, you actually have to, the enemy is now moving at an angle of 120 degrees off your position. Or let's say 130 degrees. So move 130 degrees counterclockwise. Okay. Okay, so what would be the new position be? That would be 190 degrees, which is somewhere slightly above this, right? So this, sorry, let me redraw this a little bit better. So this is my line, that my fixed axis, if you want, and so my new thing would now be somewhere here, right? So my cannon would now be facing this way. So this is the direction of my cannon, and this is the 190 degrees that I'm talking about. And then I get the instructions that the enemy has moved another 200 degrees counterclockwise. So move another 200 degrees counterclockwise. So what angle are we talking about? Well, you say atom, right? So it's 200 degrees plus 190, so that is 390 degrees. But what is that, 390 degrees? I thought there were only 360 degrees. You see where we're getting at? We are, what is it that we really, what will happen? And so this, so we had the original position was here, right? So this position 1. And then the angle between these two positions, this was 60 degrees. The new angle that we did here, so this 130 degrees was this. This is 130 degrees. Now we are instructed to make a second move. This is this move here, so that will be 200 degrees. So we're gonna do 200 degrees here. And where will we end up? Somewhere here, right? So this will be the new position of the cannon after adding another 200 degrees. But what actually position is that? Because my computer, my setup says, error, I want a degree between 0 and 360. That doesn't exist, 390. So what we do, we'll say, actually it's 30 degrees. Right? Because it's we subtract 360 from it, and then we get 30 degrees. Which basically means that it is the remainder of of 390 divided by 360. But the quotient, of course, is just 1 here. Okay, so here we see that we really use this in daily life when it comes to positions. Not the only one. Here's another one. Okay, if it's let's go back to black. Suppose it is 10 p.m. Okay, and the children are waiting Christmas evening, and the father says, in another 8 hours, another 9 hours, let's make it 9 hours, another 9 hours Santa will have come. And so the children says, oh, okay, so what time is that then? 19 p.m. When is 19 p.m., Daddy? What do? We don't do it that way, right? If we have a clock here, so it is 10 o'clock here, so this is the small and this is the big one. What is, so 9 hours later, where are we then? There's no 19 on the clock. The clock has gone 9 hours further, and we would be, so let's put this in a different color here, 7 p.m., 7 a.m., right? 7 a.m. This would be 10 hours. Sorry, 9 hours. Okay, so here we see another example of where we do a regular arithmetic. In other words, it's not 19, it is 19 minus 12. That gives us the correct answer. So here we do modular arithmetic modulo 12. Okay, here it was modulo 360. Now, the annoying part of American time is that you have PM and AM, and in many places one has already done away with it, and also in the military. So in the US we call this military time, and so there it works even better, right? So if we have 24-hour clock, this is a 24-hour clock, which if you see I'm using on my laptop, you see in the top left, it's now exactly 17:00. That means what? 5 o'clock, right? 5 o'clock, what? AM, PM? I'm not getting up that early yet. It's not AM and it's PM, right? So how do you convert that? Well, 17 minus 12 is 5. Again, we do modulo 12, okay? So in a 24-hour clock, calculations are also easier. Let's do the calculation for our little guy here. So 10 p.m. in a 24-hour clock is what then? Well, that would be 22 hours, 20 to 100, they would say, right? Okay, so now you see the time has gone 17:01 in my left top corner, right? So the minutes are written in after the column. But let's work with whole times here, with whole hours, so 20 OM. And now 7 hours later, so we add 7 to it, and we get 29. But, sorry, 9 hours, we add 9 hours to it, sorry, that's 31. But again, that's not a legitimate time, military time, okay? Military people, they like their stuff really in order and everything, regulations and rules. So 31 hours, don't give me 3100, that doesn't exist. What do? Well, we subtract 24 of it, which is really finding the remainder modulo 24. So we subtract 24 and we get 700, and 700 really is 7 a.m. and not 7 p.m. Okay, so but perhaps you will say, yo, it's not really true, you just subtract 24 from it. But here is another thing. Okay, it is 10 p.m. and the sergeant, let's put it in military barracks, and the sergeant said, in another 30 hours from now, there will be a drill. Oh my God, everybody goes, when is that? 30 hours from now. So 30 hours from now, from 10 p.m. Let's do everything in military time. So military time, let's make it, instead of 10 p.m., let's make it 9 p.m. so that we have a different number here. So, or 7 p.m. So what is 7 p.m. in, first of all, let's convert. I don't need to, but let's just do it, it's easier. And there's also a reason for it, I'll explain in a sec. 7 p.m., that would be, in military time, would be 19:00. Okay, now 30 hours later, so 30 hours later, that would be, so we do, this would be, no, sorry, not quite equal here. So 30 hours later, this would correspond to 19 plus 30, that is 4900. Now that's of course not a valid time again, so what we do, subtract 24 from it, you say, well then you're still left with 25, which is still not a valid time. So we have to subtract another 24. So what we really do is 49 minus 2 times 24, and that gives us 1. So what we do here, look at what are these numbers. This is exactly 49 divided by 24 flooring, the 2. This is exactly 49 sorry, this is going to be in black, 24. And this formula here is exactly what I was previously said. This is 49 mod 24. And this is, and here we see an example where we're not interested in this number really, although it helps us calculate it, we're really interested in this number. Okay, so this is how we do, this is called modular arithmetic. And this is simply, we have been here adding a little bit, but you can also subtract. You could say also 7 p.m. and or 1900 hours. But 50 hours ago, this thing happened. When did it happen? Okay, we can do this. Now, this brings us in the realm of negative numbers, which is something I'm not so fond of, so I'm not going to do this here. I will talk about this later a little bit, but okay. So, yes, and then... Yeah, okay. So, what we now therefore will do is kind of only work with remainders, and so instead of let's get there. Okay, let's say we want to work modulo 24. Okay, thinking, for instance, military time. What are the possible hours that we can have? Well, we can have 0, 100, 100, all the way up to 2300. Is there a 2400? No. What is 2400? In military time would be 0, 100. Now, this is military time. I'm using the format of military time, but for mathematicians, why are we keeping the 2 zeros at the end? Because we are not interested in the minutes in this case. Okay, so this would be 0, 1, all the way up to 23. How this is different with our clock, PM 12-hour clock? Well, what are the valid hours here? 1, 2, 3, all the way up to 12. But even that is already sometimes annoying, because what is 12 a.m.? Is that noon or is that midnight? And the same problem with 12 p.m. So you have a little bit of a problem here. Where is midnight? What is midday? Is this problem there in military time? No. 0 is midnight. No question about it. 2300 is evening, and 2400 is the same as 0, and therefore again we're talking about midnight. So this AM PM around 12 at noon or midnight is difficult and so much confusing that very many timetables or anything that relies on the AM PM system will not say 12 p.m. When you mean it, they say 11:59 p.m. So just so that you know, we're actually talking about the next minute, but that's midnight. Okay. So what is weird, what is perhaps contradictory for humans is to have a 0. I don't know whether I remember me telling you this, that the Indians were the first to introduce 0. So, and that is why Khwarizmi, I told you about Khwarizmi, right? Who introduced algebra and algorithm. He was the first who used these zeros because it says you can calculate so much better with it. It makes it much more unambiguous to work this than with these numbers. We need 0, and this is not very, for us. It's not weird when we talk about 0 degrees. That would be just here in this position here, direct due east, right? That would be 0 here. Remember, this is how I was envisioning this drawing there. So 0 degrees is not important, it's not strange. 0, 100 hours is not strange. 0 a.m. we don't use that, okay? But the more natural one is to use the 0. But that means, therefore, if you work modulo 24, the remainders are exactly these numbers. Now, that is in fact what a remainder is supposed to be. Remember here, the definition of remainder is, where is my definition for remainder? Here. The remainder is always less than the number, the modulus. Remember, that's the divisor becomes what we now call the modulus. So the remainder, the time, the actual time, is less than 24, which is not the case in our clock system, in 12 the dials of the clock, because the remainder could be 12. Okay, so that's why this doesn't fit. The clock system, the 12-hour clock system, doesn't fit into this scheme, but the other two do. Degrees in measuring angles, as well as military time does. There are other situations, but let me not discuss this anymore. So, okay, so this means for us, when we work modulo 24, there are only these numbers that are important. How many are there? Well, that's exactly 24, right? Because we start with 0 and we end in 23. Remember, this is the way that mathematicians and computer scientists anyway start, right? We have seen this. Why very often your index starts from 0 instead of from 1. This perhaps you might originally you might think it's a weird habit, but the more you use this, you realize, oh no, that was actually smart to do it that way. So there are exactly 24 elements, and we will denote this by Z subscript 24. So Z subscript 24 refers to this collection of sets, this collection of remainders. And so now we can do operations in there. All the operations that we know, well, what we can do with integers, we can add, subtract, and multiply. Division is a problem that I will not discuss yet. We will at some point get to this division. But these three operations we can do. And how will they work? Well, we have talked about how the multiplication works. You add two numbers and then you take, so how do you calculate A plus B in this set here? And to indicate that it is an addition modulo 24, we sometimes use the subscript 24 here. How do you calculate? Well, this is, you take the actual numbers A and B, what the actual values, the natural numbers, and then take the mod of 24. Okay? But it's not only addition that we can deal with this way, subtraction also, but that's so obvious that I don't going to discuss it. But multiplication, so we can also do this, A multiply 24B, and the result is just the same. You take A, B, and then you take that product, and then you calculate the remainder of 24. Let's do that, okay? For an example, what would be 7, 24, 13B? How will we calculate this? Okay, so here are the steps to calculate. Step 1. Well, first of all, we calculate 7 times 13. Again, I'm going to pull up my calculator. I have a separate iPad just for that. That's cool, huh? 7 times 13. That's 91. Okay. Now we have to calculate this number. And remember that itself was several steps. So step 2, well, that was step 1 before. We then take 91. And what do we do? Modulo what? 24 now. So we have to calculate this number. So 91. Divided by 24, that is 3.7. Step 3 was, step 3? In step 3 we would take the floor of this number, and this would give us already this number. Remember? That is the floor of 3.7, and that is therefore 3. And then finally, step 4 is where we actually calculate the 91 mod. 91 mod 24, and that is we take 91, the original number, and subtract from it 3 times the divisor or the modulus. So that is 91 minus 72, and that therefore is 19, if am I not completely wrong right now. Okay. So conclusion, this is 19. Now notice that this number is one of the numbers that are one of the remainders that are in the set Z24. So this is again an element in Z24. 91 is not. Don't pay attention to the fact that there's a 1 and a 9 here. That has nothing to do, that's just accident, right? So 91, the original actual product of 7 and 13 is not in Z24, because Z24 has only these valid numbers. Think of it as military time, right? Of course, I don't know exactly what it means to multiply 2 hours, but okay. But it is possible to do that. And so that's basically, you are now introduced to modular arithmetic. This is what modular arithmetic is, and we're going to use this a lot. So I'm going to leave it for now, because we have almost more than an hour, I think, and I'm going to give you now homework assignments where you basically have to calculate these numbers, and remind you, I want you to do it this longer way, this in 4 steps or 3 steps, depending on what the type of question is. But you can then later verify it either using Wolfram Alpha or of one of these online calculators that have this modulo or rem function. You might need to read a little bit instructions to find out how to do that. But you can use that to verify. But I want you to be able to do this method in the several steps. And if I would ask you, I want you to show me the steps. Okay? So that's enough for our modular arithmetic, and then we're going to do more with it in the next section.